Hey there again. This is 2002 Form B, question number 2, and this one has to do with kind of a complex pendulum. This pendulum, instead of just going back and forth in a normal motion, is actually just going in a circle. But it's still a pendulum, and it's still a ball kind of going in that situation. And there is a part here for period and frequency, but a lot of this we can do without any knowledge of simple harmonic motion. For this first part, it wants us to draw and label the vectors to represent all the forces acting on the ball when it's in the position shown on the diagram. So you'll notice it's this same position that it has right here. They want to make sure the lengths of the vectors are consistent with what the forces would be. So just be really careful on this one. Um, what I'll do is I'm going to go ahead and just draw right on this diagram. So you should have a arrow pointing straight down or towards the center of the earth, and that one should be mg, and then you'll have tension, and you can make them almost the same length. I guess that's what they were looking for with relative magnitudes. They just didn't want you to have a really short arrow here and a really long one here. So at this point, we actually have 3 points. You get 2 points for putting these, and then you get 1 point for not putting anything down that doesn't exist. So be really careful not to draw the components of the vectors, and instead just draw those two vectors themselves. For letter B, this one is worth 3 points, so this one's worth 3 points. They want us to determine the mass of the ball. We know in this situation the sum of the forces in the y direction, so that's up and down, they shouldn't change. So there's no acceleration in that direction, so the net force there is 0. In order to go through and do this, and remember we had this side, and now we also have this one. This is mg, this is still t, and then they had given us an angle also. And that angle, you can kind of see it back up on the top here, so I'll move back up. But the angle is just the angle to the vertical. So we'll move this back down to our diagram so everything fits back again. Oops, there we go. And at this point, we can go ahead and draw some other lines here. Let's go ahead and let's make the vertical line, and let's go ahead and make the horizontal line, because we've got two components for this T, and the angle that they gave us was right here. We want to know what's the opposite of the mg according to the tension. So that would be this side. This side is T times the cosine of the angle, because this side obviously is a hypotenuse, and this is the adjacent side, so we can just say T cosine of the angle will be the side that opposes the mg itself. So at this point now we can go ahead and write in our equation. Sum of the forces is equal to 0, so we're going to say T cosine of the angle, which is this side, minus, now here's our opposite side, mg. That should be equal to 0, which means that m, if we solve here for just m, that'd be equal to T cosine of the angle, and that is all just divided by g. So that one was pretty easy, and that was worth 3 points. You don't have to draw the diagram at all. You just have to make sure that you have this, this, and then you rearrange for m. Next thing they want us to do is determine the speed of the ball. So we want to find the velocity. We know the centripetal force of this ball should be equal to the tension, so that's T sine of the angle. Remember in the last one we did T cosine of the angle, so let's go back and draw this again. Remember our force is directed towards the center, that's the centripetal force. Here is our angle. So now instead of, and remember we know tension, instead of finding the adjacent side, we're finding the opposite, hence why you see Fc is equal to T sine of the angle. At this point, the centripetal force, remember, is mv squared all over the radius, and that should be equal to T times the sine of the angle. We can now eliminate the tension or the mass using the part B answer. And so we can go through and just say mv squared over r is equal to, and if you remember, our T here, well, our mass really was equal to t cosine of the angle all over g. So if we solve this for t, it would just be t is equal to mg over the cosine of the angle. Now we can plug what we have right here in for the t, and we have mg sine of the angle all over the cosine of the angle. And sine over cosine is tangent, so that's just equal to mg tangent of the angle. We're going to substitute in, we're going to say that r, if you remember, r should be equal to the length times the sine of the angle. So now we're going to have the same drawing. We know that the radius, so this side, should be equal to the length times the sine of the angle. So that's where this comes from, this little guy right here. And we can substitute it in. So we have now mv squared all over L times the sine of the angle. And that's equal to mg times the tangent of the angle. And now we can just go ahead and substitute and solve for v. So our v should be equal to the square root of g times L times the sine of the angle times the tangent of the angle. Notice that your masses do cancel here. So we just move this whole thing over to this side, and then we took the square root of that in order to get rid of the square. So that is your answer for determining the speed of the ball. So it's getting a little bit more complex. Another one of these problems that does not have any numbers in it. Next thing they want us to do is determine the frequency. Remember, part A was worth 3, B was worth 3, C is worth 4. So D just wants the frequency. We know that the period for this thing is 2 pi r all over the velocity. So you could also say the frequency then is just the inverse of that. So that'd be the speed over 2 pi r. I'm using f instead of v with this little line on it because it just makes it a lot easier to understand. Now what we have to do is substitute the velocity in right here. So we're going to have the frequency is equal to the square root of g times L times the sine of the angle times the tangent of the angle. And we're going to divide that by 2 pi. And then remember L, sine of the angle, is what we got for r. So we've substituted both the v and for the r so that everything is in the right spot. So suppose the string breaks as the ball is in a circular path qualitatively. So no numbers. Describe the trajectory of the ball after the string breaks, but before it hits the ground. So the original velocity here we know is all horizontal. Okay, so there's no vertical velocity yet. So if I was to cut it right here, this ball would start to fall this way. Okay, so its original speed would be in that direction. And the trajectory should be parabolic. So even though it doesn't have any speed originally in the y direction, it does in the x, but then gravity takes over and starts to pull it down. So you do have a parabola or a parabolic motion. And that is the other part to this problem. So that's a 15-point problem altogether. Once again, to go through the points, 3, 3. Speed of the ball is 4. Frequency was 3. And then for letter E, you had to have all horizontal speed to begin with, and then it should travel in a parabolic motion.